be quite honest with you, I feel like nothing is making sense.
Why don't we start out with any questions? Bailey.
I just have a couple questions on like concepts.
Okay.
So with rotational inertia, an object that has more mass, does that mean it's going to rotate faster?
Not necessarily. It's how the mass is distributed.
So when you're on the outer part, when you're away from the axis, the further you're away from the axis, the faster you'll be?
All right, there's two different concepts I think you're mentioning there.
Okay.
One is, so if you're if you just have a wheel spinning about its center, if it's rotating around at some constant speed, the farther out you are, the faster you're going, because you have a lot more distance to cover in the same amount of time. Then there's the moment of inertia, or rotational inertia, which deals with how easy is it to get it to either start spinning if it's at rest, or to stop spinning if it's already spinning.
So it's harder to get something with a larger mass to get moving than it is a smaller mass.
All right, if you were talking about inertia, absolutely. Rotational inertia is a little bit different, and I just happened to notice that we have the rotation, moment of inertia sticks over here. These have the exact same mass. All right, so they have the exact same mass. They were built this way. The difference is, if you notice that there's sort of a clear window right there, you should be able to see through. And this one has the clear window down there. So in this one, the mass is concentrated here. In this one, the mass is concentrated here. So if I spun these, I could, in theory, get them both spinning, in which case the speed at the endpoints are the same. It is possible. Now the question is, which one's easier to get moving? Well, let's just, red's got the mass concentrated in the middle, blue has the mass concentrated on the outside. Which one's gonna be easier to get moving?
The red one?
What was that over here?
I said the middle.
The middle one? Oh, when the mass is in the middle? Okay, red. All right. And this is, I'm not good enough a good enough actor here. This is just, so there's the red one, and here's the blue one. That hurts my elbow. Probably do it this way. It hurts less. So this one's harder to get moving. It's also harder to stop. So I'm putting a lot of effort to get it going, a lot of effort to stop it in order to move it back. This one is really easy. This is a greater moment of inertia, even though the masses are the same, because where the mass is distributed is incredibly crucial for rotational inertia or moment of inertia.
So that's the concept of rotational inertia, is where the mass is distributed.
Yes.
Okay.
So if the blue one had half the mass, it would probably still be harder to spin than the red one, just because the mass is so far out.
Okay.
And it's easy enough to change moment of inertia just by bringing things in. Figure skating is the classic example, when they start with their arms out like this, and they start going into a spin, and they bring their arms in. As they bring their arms in, they reduce their moment of inertia, which causes them to spin faster. And then to get out of that, you take your arms out again, increasing your moment of inertia, which consequently causes you to slow down. Under the principle of conservation of angular momentum.
They like to, in the book, between 8 and 9, they're making it sound like weight and mass are the same thing. And it's like, it's getting confusing, because I know they're not the same thing.
They are definitely not.
Well, I guess it's the way I'm reading, I don't know. So like, with the center of mass and the center of gravity.
Would be, the only way they would not be the same point would be if you're in some place where there's no gravitational field.
So like in the air, they could be the same thing, right?
Yes,
But if you're in a straight line, it's only center of mass.
typically, because right this way, I've got an object here. And big planet down here. So the gravitational pull actually is on every single point in this. Every little bit of matter in here is being pulled down. So and so on. Because of the mass, that's why there's a gravitational pull on it, because of the mass. So you can typically look at what we've been doing is when we take the meter stick and ask you find the center of mass of the meter stick, and then there's this gravitational pull that we pretend is acting right there at that spot, at wherever the center of mass is. Because ultimately I'm adding up a whole bunch of vectors here, which adds up to one big vector, which is equal to the weight. And we can treat it as acting at the very center of mass. So the center, the point at which we pretend the gravitational pull is concentrated is the center of mass.
The point where what is gravitated towards?
The point at, I forget what I just said. The point where we pretend all the gravitational pull is coming from.
Is the center of mass, or
Yes.
Okay. And that's always true?
Yes, the only time it would not be true is in bizarre situations,
Okay.
well out of the scope of pretty much anything. Yes, I could come up with I think I could come up with an idea where they are not the same, but it would involve an object that was so large that it, basically the gravitational pull on it varies significantly from one point to another. But it's just a bizarre, unrealistic situation.
So, in the book at one point it said something about like, you feel the gravitational pull regardless of where you are. So like if you're in outer space, where's your gravitational pull towards? Is it still towards Earth?
It depends on where you are in space. So the moon, for example, feels the gravitational pull from the Earth. The Earth feels the gravitational pull, well, yes, we feel it some from the moon, that's what causes the tides. But the Earth also experiences the gravitational pull from the sun, which allows the Earth to go around the sun. There are gravitational pulls between the planets. They're not significant from the point of view of us. I mean, when Mars goes by, when Mars is closest to us, it's not like we feel a little bit lighter or a little bit heavier. So any two things with mass are feeling a pull. Where it is noticed, the gravitational pull between planets is Neptune. They have a prediction of what Neptune's orbital path would be, and it goes slightly off. Not significantly, just a little bit. So the people who are studying it look very carefully, and they were expecting it here, and it's really here. So they thought, oh, what would cause that? I wonder if there's another planet out there. And so that's how Pluto was discovered, by Neptune just being slightly off of what was predicted. So those people care about those those things. The other places where people care about the small little gravitational pulls would be the people who do experiments with gravitation. And I think I talked in the video about the spring versus the fall. Not sounding familiar? I'm getting blank stares. I got a nod over there. I did talk about it.
Yeah.
Okay. So, an example of a group that would care about those small little influences.
It brought the elevator situation back up in the textbook, and it said your weight, so it was talking about how your weight does change.
All right, Hewitt contradicts himself, and it's really unfortunate, where he starts out initially talking about that your weight is the gravitational pull, and then later talks about your weight being the normal force against you.
Yes, that's what I'm saying, like from chapter 2 and 3, I'm like, this is completely different, it doesn't make sense.
Yeah.
He's like basically saying the complete opposite
Yep,
of what he said earlier.
yes.
It's very confusing.
Yeah, in one of the commentaries, I make mention of it. Yeah, I'm going by weight is the gravitational pull. And if you want to go with the normal force as apparent weight, I'm fine with that.
No, that's confusing,
Okay,
I feel like. So I say weight is a gravitational pull too, that's how I look at it.
and I thought, well, has the definition changed? And I looked a couple places and no, Hewitt has just went off on his own. It's like in one of the chapters that we aren't doing, he talks about weight density. This is the only textbook where I've ever heard any mention of the term weight density instead of just density. All right, other questions? Brianna?
With question 2 on 8 and 10, the two marbles, same equal mass, size, texture, racing down a sandy hill. What difference does that make from the first one with the smooth track?
All right, so if I have two objects, same mass, different distribution of mass. Because the one with the hole has more mass towards the outside. Which one will have a smaller moment of inertia? Or rotational inertia?
A smaller one?
Yes.
The one without the hole?
All right, because more mass is towards the center than the
Yeah.
other one has. So which one's gonna be easier to get moving?
The one with the hole? No, not the one with the hole, the one without a hole, cause it's in the center.
Right, okay. So the one without the hole is easier to get moving. So if I've got a nice, ideal, perfect track, no slipping whatsoever, the one without the hole is gonna be easier to get moving, and so therefore it will go faster. Now, the second problem is we're dealing with more realistic, there's now things in the way. So, well, taking the two examples here, I've got the red one here, which has the lower moment of inertia, and the blue one with the higher moment of inertia. This one was much easier to get moving. Which one's easier to stop?
The red one.
So the one with the lower moment of inertia, easier to get moving, also easier to stop. So in the first situation, there are no obstacles, it's moving fine, but in the second situation, there's now obstacles. So which one is just gonna plow through them, and which one is going to be affected more and slow down more?
The whole one will push through. But why?
Pardon?
But why? I feel like
Because
I'm not
the weight's
understanding
not
why.
centered? Kind of, that's vague.
Because the rotational inertia is more for the one with the hole.
Okay.
Therefore, it's harder to get starting to roll, but it's also harder to stop rolling once it gets rolling.
Okay, I see.
And if you watch the marble races, you can see this, and then you can see it again and again. As red number 3 comes from behind.
What about the number 7? What would the radius of the moon need to be in order to become a black hole?
That one, you have to look at the hints about where that formula is. It's the Schwarzschild radius that you're looking for. I'd have to derive it again. But the formula, so that comes g over mass of the central object times 2 I think that's the formula for short shield radius. Is it? Okay.
You didn't post the hints document.
Pardon?
I said you didn't post the hints
I guess it
document.
makes sense. Well, I mean, yeah,
The hints document, you're supposed to read my mind.
harder to get started, but also harder to start.
But he goes over it in one of the
Wait,
videos.
for 8, 9, and 10?
So for the radius to be a black hole,
But it's just in
It-
gravitation.
that's the formula for the radius of black hole.
So what is C?
That's full. And
Speed of light.
go through the same process, same place, but it's not as.
M is the mass of the object. And big G is the gravitational constant.
That's the formula for which number?
7.
So apparently at least two things I haven't posted. And once again, you disappoint me by not reading my mind properly.
What is that, R?
BH for black hole.
Okay.
It-
Obviously, I should.
Schwarzschild was a German physicist caught up in World War I. He got nailed in a mustard gas attack and was recuperating in the hospital. And while doing that, general relativity had just come out like 1 or 2 years prior to this. And so he worked on general relativity. Now, the derivation that I typically do in class is a classical derivation, not using general relativity, but to get to the same result. So ultimately, he dies because of his injuries. But he did manage to publish 2 papers before he died,
Should've just watched Netflix.
if only.
I have another question.
Yes,
On the lab, the, work energy theorem one, it shows all this stuff on the back where the change in K equals K final minus K 0 equals KF equals, you know what I'm talking about?
yep, what's the question?
The question is, so when I use this, I'm finding the change in K, not the final. There's just a lot of equals.
Yeah, all right,
I'm
so
confused as what this is solving.
in that lab, basically it's the total work or net work is equal to the change in kinetic energy. This is what we're trying to see if it actually works or not.
The theorem.
Yes, this is the work energy theorem. So we find the work here by force times displacement. Because we have 2 forces involved, we have the force of two force of gravities involved, one doing positive work, one doing negative work. The difference between the magnitudes or 1 plus the negative, there's a positive and a negative number you add together. The change in kinetic energy, well, the formula is for kinetic energy, as all of you know, 1/2 mv squared. But to get the change, it is whatever the final kinetic energy minus the initial kinetic energy is, because that's what change is always final minus initial. But the initial kinetic energy in each of the cases is 0. Because they're not moving. To start out with, they were hanging like this, you move the hand out of the way, and then it starts to move. So the initial speed is 0, so therefore the initial kinetic energy is 0. So this is 0. So what you're left with is K final minus 0. And so the kinetic energy that you find is,
The final.
it's the final, which is also the change because we started at 0.
Okay, so those two should be the same.
Yep.
Okay, thank you. That makes sense.
Okay,
when you're calculating the percent difference between work and delta K, I wasn't sure what should be on the bottom, or we should divide the difference by.
Alright, so when you're finding the percent error or percent difference,
Percent difference.
alright. Percent error, there's a correct answer. Because you find the work and you find the kinetic energy independently, you know, you don't know which one is correct. So that's why you're finding a percent difference. So percent difference is the difference between the two, which I ask you to find,
Yeah, I found it.
and divided by the average, which I also ask you to find. So whatever you have for the difference, and then for the average, I just divide those two numbers and then put it in percent form.
Okay, got it, thank you.
I do not know why on this lab, I'd probably have to go back and look at the original one, but I don't know why on this lab I don't just say, what's the percent difference? But instead I have you work through the numerator and the denominator and then figured you'll just divide them.
Okay, just to make sure, for, I guess, for the results for the second chart, what do you want me to do for the FG1? If you,
But you said FG1?
yes,
In, my copy here. Thank you. Yeah, if you understand the George speak, you can pick it up right here. The magnitude of the force on the system from M1 and M2. What I'm looking for here is the weight. So that FG1 is just the weight of object 1, or mass 1, which is just mass 1 times G.
okay, that's it,
And then FG2 is mass 2 times G. Yeah, that's it.
okay,
Yeah, I decided for some reason to call it something a little bit different than I had previously.
okay.
There are a couple eccentricities on this lab that I really don't know why, and I just haven't gone back to change it into the standards that I have been using.
Okay, and then for the final question on the second page, when you're supposed to figure out what would be the necessary time to get a 0% difference,
Yes,
for that velocity, you wouldn't use the usual velocity, you'd use 2h/t.